The big question is how to decide these weights. To answer this question, let us take another look at the same example of two options. We have A and B as our two options. They have played 10 games, out of which A has won 9, B has won 1. The corrected numbers are 9 plus 1 equals to 10 in favor of A, 1 plus 1 equals to 2 in favor of B. The scores were therefore 10 by 12 in favor of A, 2 by 12 in favor of B. There is another way to get to the same answer. Let us design a dynamical system to compute our scores. We have two states A and B. At each time, we will either be standing in state A or standing in state B. We decide to stay where we are or we decide to change our state at random. The rule of these random movements are as follows. If you are at state A, then we stay at state A with probability 10 by 12, or we go to the B with probability 2 by 12. If we are at state B on the other hand, then we stay at B with probability 2 by 12 and go to A with probability 10 by 12. We run this experiment for a long time and observe the fraction of times we are in state A or fraction of times we are in state B. These fractions are scores of A and B respectively. Effectively, we have designed what is called a Markov chain over two states A and B. The transition rules between these states were designed so that the fraction of time spent in A and fraction of time spent in state B in the long term were precisely equal to 10 by 12 and 2 by 12 respectively. If we carefully examine the transition rule, it suggests that fraction of time spent in state A equals 10 over 12 times fraction of time spent in A plus 10 over 12 times fraction of time spent in B. Since fraction of time spent in A plus fraction of time spent in B is equal to 1 by definition, we have that fraction of time spent in A is equal to 10 by 12. Voila! Now this gives us a general approach to design weights we were looking for. In general, there are more than two options. To explain this, let us start with simple case of three options first. A, B and C. How creative! We can create a graph of these three nodes, a node each corresponding to each options. As before, A and B have played 10 games, of which A has won 9, B has won 1. For B and C, they have played 4 games, out of which each one of them have won 2 each. For A and C, they have played 6 games, of which C has won 4, A has won 2. As before, we can set pairwise corrected proportions for each of them. A versus B would be 10 over 12 in favor of A, B versus C 3 over 6 in favor of B, C versus A 5 over 8 in favor of C. Alright, so we got our data. As before, we want to design a dynamical system, a scoring machine, where we can walk between states A, B and C. At each stage, the rules of the transition to the next state are determined by which state we are standing in and the other state to which we want to jump. This utilizes the outcomes of pairwise games. For example, if we are currently at state B, next time we will be at state A proportional to 10 by 12 and at C proportional to 3 by 6. That is how often A defeated B, and therefore we will go from B to A proportional to that number. And that is how often C defeated to B, and that is why we will go from B to C that often. To make sure that these numbers always add up to less than 1, we will multiply all of these numbers by a third. This normalization number, that is 1/3 here, is obtained by looking at maximum number of neighbors any node or any state has in this graph. In our case, all 3 nodes are connected and hence it's 3. Once we have this, we get the following effective transitions. When we are at B, in the next time we go to A with chance 10 by 12 times 1/3, which is 5 over 18. We go to C, 1/2 times 1/3, which is 1/6. And then we remain at B rest of the time, which turns out to be 10 over 18. In a similar manner, we can design rules for A and C. In particular, if we look at transitions from A to B and C to B, the transition rates should turn out to be 1 over 18 and 1 over 6 respectively. This gives us a weighted formula. In the long run, the fraction of time spent in B is equal to 10 over 18 times fraction of time spent in B plus 1 over 18 times fraction of time spent in A plus 1 over 6 times fraction of time spent in C. That is, rearranging this term, we obtain fraction of time spent in B equals fraction of time spent in A plus 3 times fraction of time spent in C, all divided by 8. Similarly, looking at A and C, we get two more such equations that relates the fraction of time spent in each of these states. The weights are coming from the relative wins and losses between the options or teams. These fractions will be the scores of options. Examining the equation for score of B again, score of B equals to 1/8 times score of A plus 3/8 times score of C. This score naturally incorporates the fact that score of B is 3/8 times the score of C and 1/8 times the score of A. The weights are coming from how often B has been relatively victorious over A and C. And if indeed score of C will be high, then score of B will be high, and vice versa. As we can see, when there are more than 3 options, the rules can be defined in a very similar manner. The resulting ranking algorithm that we just learned is called rank centrality. Recapping the algorithm, it is computing scores as follows. We have a network of states, each correspond to possible options such as sports team or restaurants. A pair of nodes have connections between each other if they have been compared once or more. At each time step, we are at one of these nodes in our machine and we transition to any of the neighboring state next time with probability that is proportional to how often that neighbor has defeated us, the current state. So we are likely to go towards the winners more and less likely to go towards losers. And then we assign the score of each node as the fraction of time we spent in that particular node as per this dynamics in the long term. In the language of Markov chain, this fraction of time is called the steady state distribution of thus designed the Markov chain. Given this algorithm, a restaurant that is new but has been compared very favorably to an old well-known Michelin 3-star restaurant might have a very high score and thus resulting into really meaningful scores. In summary, in this section we have discussed the following topic. In many scenarios, the preference data available is not necessarily ratings. It is comparisons, such as those in sports. Comparisons are more absolute way to capture preferences compared to ratings. Comparisons can be easily derived from ratings. When preferences are comparisons, obtaining global ranking from them is not easy. Condorcet paradox is a nice example that explains this difficulty. We discussed a simple fraction of wins as a scoring rule to decide ranking. Naturally, it turned out to be too simple and it needs weight adjustment. We used a dynamic system, a machine, also known as Markov chain in probability, to design such an adjustment. The algorithm that we described is known as the rank centrality. In the process, we also touched upon the questions of what is the chance that sun will rise tomorrow? And if it indeed does, we will see you in the next section and we'll discuss how to move beyond this simple algorithm that is just based on population view and start making algorithms really personalized. Thank you.